Hello. Now, assuming you're already familiar with a simple graph, I'm going to talk about the degree of a vertex as well as an R-regular graph. The first example I'm going to give here is we're going to consider the complete graph on 3 vertices, which is also the cyclic graph on 3 vertices here. The degree of a vertex is the number of adjacent vertices. So if I consider this vertex here in green, we can see that it is adjacent to these 2 vertices. And if I were to add one more vertex here, we can see that as there is no edge connecting our green vertex to our orange vertex, they're not adjacent. And if I were to add an edge here so that that orange vertex isn't isolated, our green vertex is still not adjacent to our orange vertex because they're not directly connected by an edge, right? Now, the other way to think about this, and what I find is actually more helpful in terms of directly seeing this, is if I were to draw a little circle around my green vertex, and I'm going to do this in red here, we can ask ourselves, how many times does that red circle cross an edge? And we can see it's twice. That'll be helpful in a moment, right? So we have that our degree, I'm just going to call that V1, right, is 2. Our degree of that vertex, V1, our green vertex, is 2. And in this example here, our orange vertex, draw the circle again, has degree 1. This vertex down here has degree 3, and this vertex here has degree 2. And if we go back to what I initially started with, where it's K3, we can see that they all, in fact, have degree 2. Now, if you're dealing with non-simple graphs, where we allow loops or parallel edges, such as in a multigraph, right, we have to know how do we deal with it. Here are 2 examples, one with a loop and one with a pair of parallel edges. Here, you should hopefully know that the degree is 1. Ask yourself now, what is the degree of our yellow vertex? If you were trying to think in terms of adjacent vertices, loops can be a little confusing. So instead, I recommend you use that circle, and you can ask yourself, how many times does an edge cross our circle? Well, one edge crosses it once, and another edge, being our loop, crosses it twice. However, that's still 3 in total. So we can see here our degree of our, orange vertex, I'm going to call this one V1, is actually equal to 3, even though there's only 2 edges. Loops can be a little confusing. Just remember, draw the circle. Now, here we have our parallel edges. Once again, here is degree 1. What about this one? Up here. Well, you draw your circle, you can see it has degree 2. Down here, we have degree 3. And that's how we handle loops and parallel edges. Now, let's consider this next one. I have drawn here a tree. This tree has several different edges. Our leaves are here. Leaves are vertices which have one adjacent vertex, which means our leaves have degree 1. Okay? Ask yourself now, what is the degree of the yellow vertex? 3. What is the degree of the pink vertex? 2. What is the degree of the blue vertex? 5. Very simple. Now, if I go back to our previous example, where we had K3 as we can see that the degree of each vertex is 2, we would call such a graph 2 regular. And in our other examples here, we can see that there are vertices of many different degrees. So these graphs are called irregular, meaning that there is no regular degree, or the vertices have different degrees, however you prefer to remember it. Now, we're going to consider these 5 classes of graphs simultaneously. Okay? On the left, we have in blue our cycle graphs. In the middle, we have with purple our complete graphs. And then the end, we have in red our paths. So, firstly, think, what is the degree when the vertices are 2? As you can see up the top here, all of them are the same. Each vertex has degree 1. They are all 1 regular. Now let's consider our second row. Firstly, our cycle and complete graphs look the same. So let's give it a go. Here we have already discovered this is a 2 regular graph. For our path, here we are also here we also have degree 2. However, as you can also see, here we have degree 1, so our paths are not regular. Yeah? This is in fact irregular. Now, we'll go down to the next step. For our cycle graphs on 4 vertices, we can see we are in fact 2 regular. And if we were to go to the cycle graph on 5 vertices, we can see once again we are 2 regular. And as you can hopefully expect, particularly if you are more familiar with cycle graphs, every cycle graph will be 2 regular. For our completes, we have before, in our case where it was 2 vertices, we were 1 regular. For 3 vertices, we are 2 regular. For 4 vertices, we are 3 regular, which is sometimes referred to as cubic. And in the case of 5 vertices, we have 4 regular. And as you might expect, with complete graphs, we are always 1 less than the number of vertices in terms of our regularity. And every complete graph is regular, just like every cycle graph is regular. For our paths, although we get these nice degree 2 vertices over most of the path, there are always these degree 1 vertices, which will mean that a path is irregular once you have a total number of vertices greater than 2. Now, on to our next example, the Peterson graph. Consider the Peterson graph. Ask yourself, is it regular? Look at each vertex. Now, you should hopefully see it is in fact cubic, or 3 regular. Quickly to remind you, because it's the one thing I find most people forget, our parallel edges and our loops, when you're in doubt, simply draw the circle and count the crossings. 1, 2, 3, degree 3. When you're in doubt, draw the circle, count the crossings. 1, 2, a parallel edge, degree 2. That's it for regular graphs and vertex degrees. Thank you.